Good day, class. Now we will derive the rotation matrix of from our previous topic, which is rotation or orientation matrix. Okay, so we will derive R01. We will derive the rotation matrix of R01. So to derive the rotation matrix of R01, we will use the principle of projection and the process that we did to obtain Z rotation matrix. Okay, but now it will be different because our mechanical manipulator has frames that are separated from each other. Okay, so first, to derive the rotation matrix of R01, we will look at the frames of frame 0 and frame 1. So let's draw a square here, a dark blue square. Okay, so what we will observe here is the placement of our rotation angles. So we have here theta 1 and theta 2. So we will look first at theta 1 because it is the first rotation angle. Okay. So theta 1 is the rotation angle of frame 0 and frame 1. Okay? Frame 0 and frame 1. So if there is a rotation at frame 0, frame 1 will move, just like here. Okay, in this our previous example. But now they are separated. So we will do a different, we will do a bit different method. Okay, so we will look where theta 1 is indicated. So it is at the axis of Z sub 0. Okay, so if we recognize where theta 1 is indicated, or where we will rotate, okay, so it is a so it is at Z axis, we will use our derived Z rotation matrix because we have a rotation at the z-axis. Okay, so this is already z0, x0, y0, z0, x1, y sub 1, and z sub 1. Okay, so we will have a rotation at z-axis. So we will use the derived z rotation matrix. Okay, so with this z rotation matrix, we need also a rotation matrix if the joint joint 1, because the theta 1 is at is indicated at joint 1 at z axis. We need a rotation matrix if the joint is not moving, because this z rotation matrix is a rotation matrix if the joint is moving. Okay, if the joint is moving, so we will call this z rotation matrix a moving matrix. Okay, a moving matrix. Okay, so this will be derived first. Okay, so we need a rotation matrix that describe the joint if it is not moving. Okay, this is a rotation matrix, but it is a stationary rotation matrix, so not moving. Okay, not moving rotation matrix. Okay, so we need that to obtain the rotation matrix of R01. Okay, so this is the stationary rotation matrix. So the Z rotation matrix is the moving or the rotating matrix. Okay, or the orienting matrix. So to derive the stationary matrix, we will use the principle of projection. Okay, so please listen carefully. So again, we will look at x sub 1 projected on x sub 0. Okay. So x sub 1 is at the same direction as x sub 0. So remember class that all sides as well as all axes, we assume that their measurement is 1 unit. Okay. Because x sub 1 and x sub 0 is at the same direction. Okay. The projection of x sub 1 on x sub 0 is no other than 1. Okay. So just like the z0, the z sub 1 on z sub 0 projection. X sub 1, the projection on x sub 0 of x sub 1 is 1. Okay, next. Let's see the projection of x sub 1 on y sub 0. So x sub 1 is at the right direction. Y sub 0 is at the back direction. So they are perpendicular to each other. So there will no uh, projection angle between them. So because of that, the projection of x sub 1 on y sub 0 is 0. Okay, the same with z sub 0 because x sub 1 is perpendicular to z sub 0. Okay, are no uh there are no orientation angles on between x sub 1 and z sub 0. Okay, next, uh the projection of y sub 1 on x sub 0. So y sub 1 is perpendicular with x sub 0. So the projection will be 0. Next, y sub 1 on y sub 0. So they are at the same direction. So this will be 1. Okay. Next, y sub 1 on z sub 0. So y sub 1 is perpendicular with z sub 0. So this will be 0. Okay. So next, z sub 1 on x sub 0. So x sub 1 and x sub 0 is perpendicular with each other. So this is 0. Z sub 1 on y sub 0. So they are perpendicular with each other. So this is 0. Z sub 1 on Z sub 0, they are at the same direction. Okay. So we have 1 unit at the projection of Z sub 1 on Z sub 0. Okay. So we have now the stationary matrix of R01. So what we will do now here, we will multiply the stationary matrix to the Z rotation matrix. So you can use the rules of multiplying 3 by 3 matrix with another 3 by 3 matrix, or let us use Matlab, okay, for our computations in matrices. Okay. So let me use my Matlab, or let me open first my Matlab. Okay. So while waiting, Matlab, if you notice that the stationary matrix is a identity matrix, okay? An identity matrix means in matrix algebra it's also considered as a 1. It means if you multiply this identity matrix to another matrix, the answer will be this matrix, the C-rotation matrix. The definition also of identity matrix in robotics is there will have no rotation if we have a stationary matrix. Okay. So let's create a script. Yeah. Let's name the script. Kinematic diagram. Rotation matrix. So let's make it an example 1. Let's open the script. Okay. So let's give this let's display a title of forward kinematics. Okay. So this is forward kinematics. Oh, this is a string. Okay, sorry. So this is a string. Okay. So first is the rotation matrix. Okay. So first, let's identify the variable that we will use, the independent variable that we will use. We will use a theta as our independent variable. So we will use the code sims and to represent theta, sorry, this is not theta, this is theta 1. Okay, based on our rotation, this is theta 1. Okay, so here's one. Okay, theta 1. Theta 1, sorry. Theta 1. Theta 1. And theta 1. Okay. So we will use T1 as our theta 1, as our variable theta 1 in our Matlab code. Okay. So first, our variable R0 underscore 1 for R01. So we will make a matrix. So to create a matrix, we will use square parenthesis. Then our first row, 1, 0, 0, we will just type the element of the first row. Then for each element, just use space, okay, to write again a new element. Then after the row, uh, put a semicolon. Okay. Then you can now proceed to the second row. 0, space 1, 0, semicolon, then 0, 0, then 1. Okay. So this is already a matrix. If you run this, so F5, okay. So we have now a identity matrix, okay, or the R01 matrix. Okay. So I forgot to show the workspace. So in workspace, we have here R01 with the value of R01, and the size is a 3 by 3. So we have here a 3 by 3 matrix. Okay. So this is a 3 by 3 matrix. Next, we will multiply it to another 3 by 3 matrix, which is a z-rotation matrix. So let's build the next matrix. So I will use 3 dots and enter to continue the equation, the R01 times R12 equation in our code. So here, this is again square parenthesis, then cosine, close open parenthesis T1. Okay. Then negative sine, close open parenthesis T1. Then 0. Okay. Okay, semicolon. Then second row, sine T1, cosine T1, then 0. Okay. Then semicolon. Okay, next is 0, say 0, space 1. Okay. So our z-rotation matrix is coded. Okay. So let's check what will be the answer. So identity matrix is equivalent to 1. So 1 times the rotation matrix. So the answer should be also this. Okay. So let's press F5 or click the play button. Okay, we will have cosine T1, negative sine T1, 0, sine T1, cosine T1, 0, 0, 0, and 1. Okay, next. So this is for R01. So we can make this pretty R01. Okay. So let's see the difference between a regular matrix and a prettified matrix. So this is the regular matrix and this is the prettified matrix. Okay. So let's put some semicolon. Sorry. So CLC. So let's put some semicolon after the R01 matrices. Okay. So that it will not mirror after we got the R02 and when we solve the, sorry, when we derive the R12 and solve for R02. Okay. So that is the creation of matrices in Matlab. Okay. So let's proceed to our second rotation matrix, which is R12. Okay, R12. So if you notice, class, the frames from frame 0 up to frame 2 are the same. The axes of each frame are pointing to the same directions. Okay, so it means that the R12 is the same with R01. Okay. So this is only true in this design of mechanical manipulator. This is only true in this design in this design of mechanical manipulator. It means if the design was changed, if the design is like this, of course the process will not be the same. Okay. So if you if you learned and understand the DH frame rules, you will understand why we have frames with the same direction of axis and frames which do not have the same direction of axis. Okay. So because these are all the same, we can copy this for R12. Okay, and change this into R12. So we will not repeat it for the sake of a short video. For the sake of a shorter video, and okay, then we will change our theta. It is not theta 1 anymore because our angle of rotation is at z sub 1, and it is now theta 2. Okay, so let's replace theta 1 with theta 2. Okay, this is theta 2, this is theta 2, this is theta 2. Okay, now let's go back to our Matlab. Let's go back to our Matlab. Okay, so because R01 is the same with R12, I can control C and control V this. Okay, so if you are programming, prevent using control C and control V. Okay, except if you have redundant program or redundant code, you can use control C and control V like this. Okay, so let's identify our second variable t2, then change from r12 to from t1 to t2. Okay, this will be t2, this will be t2, and this will be t2. R1. So now we have R12. We can now do our equation. So R01, okay, multiplied to R0 unders R sorry to R1 2. Okay. So before pressing F5, let's clear all to make sure we don't have values at the workspace. Then CLC. Okay, then let's also make it pretty. Okay, so R02, R0 underscore 2. Okay, so F5. Okay, so the answer should be at the command window. Oh, it is oh, it's print. Okay, there's an error again. Clear all, CLC. Okay, F5. So we have here, let's make this bigger. Okay, in our command window we have the R01, the R12. Okay, the product of R01 times R12 and the prettified. Oh, this is not prettified. Prettified R02. Where's the prettified R02? This is not prettified. Oh yes, this is the prettified RC2. R02, it's not the same. Oh, it's not. Yes, it is the. Oh, it's not the prettified, sorry. Again. Clear all. CLC. Okay, again. So display forward kinematics T1 T2. Let's make this R02 is equals to R01 times R12. Let's put some semicolon. Okay, and then see what it will be look like. So F5. Okay, now we have a prettified R02. Okay. So this is the rotation matrix of the whole mechanical manipulator. Okay. Now we have the 3 by 3 matrix or the rotation matrix of our mechanical manipulator. Now we will do some substitutions of value, okay, to our variables T1 and T2. So we have here two types of values, radian and degrees. So because these are rotation angles, the default unit is radian. So we will make it degrees later. Okay, so let's create here radian. Comment radian, then let's give T1 as a value of 0 first. Okay, so the units are radian, then T2, 0, also 0, test it with 0 values first. Then let's copy, or before we copy this, let's make pretty R01, pretty R12, and pretty R02 comments. Okay, then let's copy this from R01 up to pretty R02. Then put it under the value of T2. Next, let's create another percent degrees for the unit of degrees. Okay, so T1, let's also make T1 0. Let's also make T2 is equals to 0. 0 degrees. What 0 degrees? Then let's copy this again and paste it under T2. Then because the unit at this area, at this section is degrees, we will add letter D at the trigo functions. Okay. Let's add letter D so that it will convert the radian angles, because the default of this of a Matlab is at radian. So to have a degree unit, we must add the letter D, okay, to each trigo functions. Okay, so what will happen here? So this will happen first. Okay, the algebra form, or the algebraic form of our rotation matrix. Then with the values, with the radian values, okay, it will solve that rotation matrix with the radian values. And now for the last thing will happen is the radian is the computation of rotation matrix with degree values. Okay, so if we press F5, sorry, it will not run. It will have no output. Okay, remove the semicolon at R0, at both R02. So if we run this, okay, R02 is an identity matrix. The same with R02. So it means that our mechanical manipulator is not moving because the rotation matrix, okay, of the mechanical manipulator is identity matrix. Okay, based on the computed rotation matrix. Okay, from the start and then up to the the substitutions of T1 and T2 values. Okay, so let's also make this visible. This R02 equals to R01 times R12 of the algebraic expression of our rotation matrix. So let's make this sorry, this is not Python. Okay, algebraic expressions. Okay, next. So clear all. Let's clear them all, then CLC. Okay, let's change the values of T1 and T2. For T1, let's try pi over 2. For T2, let's try negative pi over 6. Then for degrees, so pi over 2 means 90 degrees. T2 for T2 is equals to negative pi over 6, so it means it is negative 30 degrees. Okay, so let's run this F5. Okay, so at the command window, we have same answers for R02 for R02. So they have the same answers. They are in decimal form. Okay. So let's prettify the last answer for degrees. So we can have a much prettier answer. Okay, so let's make it fraction. Okay. So let's remove the percent at the last. Pretty, then add sim, sym, close open parenthesis, the R02. Okay, then, okay, this is the last pretty at the degrees. Okay, then sorry, oh yes, then F5. Okay, so this should have a fraction elements inside the 3 by 3 matrix or inside the rotation matrix. Okay, so R02, this is the algebraic expressions inside the rotation matrix. Okay. Then next, the answer when the value is changed at the radian section. Okay. And at the degree section. Okay. So when prettified, we have fractions on each element. So we have 1/2, negative square root of 3 over 2, then 0, then square root of 3 over 2, then 1/2, 0, then 0, 0, 1. Okay, so this is the rotation matrix. Okay, again, the use of rotation matrix, you this is what you solve or change to make your mechanical manipulator orient, to make the end effector orient, and to move the revolute joints of your mechanical manipulator. So if I test other rotation angles, so clear all, CLC. If we test another rotation angle, so for example is pi over 4. So let's test pi over 3. So pi over 4 is 45 degrees. Then pi over 3 is 60 degrees. Okay, so please review your trigonometric your trigo subject, try to review the rotation angles. Okay. Then F5. Okay. So this is the answer. Okay, this is at decimal. This is at fraction. So the fraction is not pretty. Okay, so let's go to the decimal. So this is the rotation matrix. Okay, when the 21 is equals to 45 degrees and T2 is equals to 60 degrees. Okay, let's test another value. So let's test uh, 270. If you don't know the radian in terms of pi of 270 degrees, so just multiply it with pi, sorry, multiply it with pi, then divide it with 180, or just use a calculator. Okay, so 270 270 divided by 180 is equals to 3 over 2. So just change this to 3, and this is to 2. So this is 270 degrees. Then another one, negative pi over 2. So this is 90 degrees. Okay. So this is 270 degrees. And this is negative 90 degrees. What is negative 90 degrees? Isn't negative 90 degrees is also 270 degrees? Okay. Isn't negative 90 degrees is also 270 degrees? Okay. So it's the same. It's the same. Negative 90 degrees is also 270 degrees. They are all. So please review the rotation angles and their conversion from radian to degrees, then degrees to radian in terms of pi. Okay. So let's press F5. Okay. So the answer is this. So as you can see, it looks like a, a it looks like an identity matrix, this one. Okay, but it is not an identity matrix. Okay, it's not an identity matrix because the one must be positive. So this is not an identity matrix, but this is the rotation matrix if the value of T1 is 270 degrees and T2 is negative 90 degrees. But 270 degrees and negative 90 degrees is same. It's the same. They are both 270 degrees. Okay. So that is rotation matrix. Okay. So this is rotation matrix for this model. So there are different rotation matrix, different derivation for each mechanical manipulator. So we will discuss some examples like the assignment of frames for next videos. Okay.